So what we're going to look at now is questions where we don't actually know what the population mean and the population variance are. We said before in the lesson, if we were measuring all the leaves on the tree outside, we wouldn't actually know what the population mean and the population variance is. We would not have measured every single leaf on there, and we were dealing with samples. So what we are going to do now is we are going to just go through some notation first of all. What is mu? Mu is the population mean, yeah. And what is x bar? The sample mean, yeah. What is sigma squared? Population variance, yeah. What's the fourth thing you think is going to appear in this list? Okay, what in the wordy bit? What will that be? Yeah, the sample variance. Sample variance I'm going to call S squared. Okay. Now, what we are going to have after that notation is this. If we don't know mu, we use what? If we don't know mu, what do we use? The sample mean, yeah, we use x bar. Okay, if we don't know what the population mean is, we have to use the sample mean. And it turns out that if you take lots of sample means and find their expected value in the long term, you get mu. Now there's a whole 3 pages of proof I could go through, and it's in the book, and I did go through it one year with a class, but to be honest, you don't need to be able to reproduce the proof yourself, and if you want to have a look at it, it's in the book, or I can give you some notes on that later on. But because of this fact here, because the expected value of this is this, that means that we call x bar is an unbiased estimator for mu. Now then, in the book there's a definition of what an unbiased estimator is, which I'll just flag up for you in a minute. We only want an unbiased estimator for something if we don't know what the something is. So in the book there's this sort of grey box definition down here that if you've got some unknown parameter alpha, if you can find something else, an estimate for it, where the expected value of the estimate is what you are trying to estimate, then that estimator is called an unbiased estimator. Okay, so very fortunate if we're trying to find an unbiased estimator for mu, the population mean, we can use x bar. That's fine. There's another bit of notation now, which is this: mu with a hat over it. Okay, the hat means an unbiased estimator. So that is notation for an unbiased estimator for mu, and mu hat is x bar. Okay, nothing groundbreaking, nothing particularly earth-shattering in that, but our unbiased estimator for the population mean is our sample mean. So what we need to know now then is, if we don't know sigma squared, what do we do? Well, we have to use our unbiased estimator for sigma squared, so I'm going to write it like that first of all, sigma squared with a hat over it. And sigma squared with a hat over it, the unbiased estimator, is n over n minus 1 times by s squared. So it's almost the sample variance, but there's this fiddle factor of n over n minus 1 in there as well. And it does turn out that the expected value of sigma squared hat, or in other words, the expected value of that is sigma squared, is an unbiased estimator. It's okay to use it. In the long run, its average is sigma squared. Now there is proof of that. Proof of it is particularly nasty, and it takes about 3 pages. Okay, it's sort of a nasty page of expectation algebra, followed by another nasty page of it, followed by something else as well. I'm not going to go through it with you now. It's in the book. If you want me to go through it or lend you that at some point, I can do. That's absolutely fine. So, what I want to do now is just put some flesh on this by doing an example and showing you how you work out these things and how the calculator works things out for you as well. Now, your calculators are all far more complex than mine, but as a little test, if we had these values, 3, 6, 7 and 8, then I ask you to work out the population standard deviation, you should be able to find a way of inputting those numbers in your calculator and probably finding a button something like that which gives you an answer, or it might say sigma xn, something like that. That will give you the standard deviation of those 4 numbers, and you are looking for a value of 1.8708 if you have found the right buttons. Okay, different calculators, different ways of doing it. You may have to put it into a list, you may have to put it in standard deviation mode. Okay. So we've got that out of the calculator. We also need to know, if we had this and this was our sample, how to get the other one out, sigma hat, which what we said a minute ago was n over n minus 1 times by s squared. Well, it will be square rooted here because I'm just doing sigma. So it'll be that calculation. Now on your calculators, that one I just saw a minute ago actually had the SN. Yeah. You are looking there for that one for 2.1602. Okay, if you press the right button. Some ones calculate a minute ago, I think it was marked SN. It may also be marked sigma n minus 1 or sigma x n minus 1. Any of those things. But it should be, from what we said earlier, it was n over n minus 1 s squared, what we square rooted here. So it should be 4 things in our list, 4/3 times by your other one squared, square rooted. And if you do that calculation, you should also get that number. So I just wanted you to make sure you can get both of those out of your calculators. Okay. Right, now we know how to use a calculator. If we look at an example, we've got a population with an unknown mean called mu and an unknown variance called sigma squared, but we do have 10 values. We have a sample of size 10 with these 10 values, and the question may ask you to find unbiased estimators for mu and sigma squared. Okay. So in the notation that we are just used, that would be a case of finding mu hat and sigma squared hat. So I know you're furiously scribbling, but mu hat, what did we say mu hat was equal to earlier on? X bar, which is the sample mean. So if you bung those numbers into your calculator and say what's the sample mean, you will get that. And unbiased estimate of the variance, you should now know how to get that from your calculator as well. Okay, so it's just a case now of coming up with those answers from the calculator, and then we'll also show you in a minute how to do the sigma squared hat one sort of old-fashioned longhand way. So if you can get those out of calculators, fine. If you can't, let's go back and do this the old way a minute. So what was the formula we had earlier on for getting sigma squared hat? It was n over n minus 1 times by s squared. S squared, what was S squared in words? In words, what was S squared? The sample variance, yeah. Okay. Right. If you didn't have a calculator which gave you the variance, how would you go about finding the variance of those numbers up there? In other words, the sample variance, how do you go about finding a sample variance if you haven't got a button on a calculator which just tells you what it is? What formula did you do in S1 to find the variance of a set of numbers? Say? Yes, we could have that. Could you give it to me in a more basic version with sigmas in it? So if I started it off like that, what have I got to do to get... I'm not looking for probability things.
1 over n sigma x squared.
Yes.
1 over n sigma x.
Yes, which is the same as putting the x
one
part
of
in
the-
there. Yeah, okay. That's the formula I was just looking for, okay, from the dim and distance past for the sample variance. Okay, so that is what S squared will be. So, we know at the moment that x bar is 10. We've got that from our calculators. Your calculator should also report to you, if you press the right buttons, what sigma x squared is. Can you? 1028 is correct. And what is n in this example? How many numbers do we have? 10. Okay. So if we now work out then what s squared is from using this, that is the 1028 over 10, take away 10 squared. You can do that in your heads because the numbers are so nice. 2.8. Yeah. Okay. So if we know what s squared is, what did we say sigma squared hat was equal to? N over n minus 1 s squared. So this is where the n over n minus 1 comes from. If you had been, for example, given some summary statistics in the question, instead of being given the original data, if you were told what sigma x squared was and sigma x was, you could go and do it this way. So this should be 10 over 9 times by 2.8, and if you do that sum, you should get 3.1 recurring, which is what we had from our calculator earlier on, up there. Okay, so you may even be given a question in an exam. If you were given in an exam sigma x squared, sigma x and n, you could go and use this formula here to go and find what mu hat and sigma hat or sigma squared hat were. Okay, it's just showing you can do it that way as well. Right, one more bit of notation I just want to make sure you have seen, and that is a phrase. It's on the homework sheet, somebody picked up on it earlier on. It's the standard error of the mean, if you ever see this phrase. The standard error of the mean. You just need to know what that phrase refers to, and it refers to the standard deviation of x bar. When we were doing the last lot of teaching, we said x bar always follows what distribution? Normal? Mu sigma squared over n. Yeah, whatever distribution x follows, we've said before that x bar follows that. Well, that's the variance there, sigma squared over n. So that means the standard deviation of x bar is that sigma squared over n square rooted, or in other words, sigma over root n. So the standard error of the mean is sigma over root n. It's the same thing as a standard deviation of x bar. Some books or some questions may refer to that, and you just do need to know what that means. So So one final example on the central limit theorem, then we're going to do some questions on unbiased estimators and things. So the question is this: if we have a large number of samples and it's a size n, that's how many samples. So if a large number of samples of size n are taken from a distribution which is Poisson 2.5, and about 5% of the sample means are less than 2.025, find n, the size of the samples. So we're doing a large number of samples, but each time we are sampling n objects. They've all come from a Poisson distribution. Well, that video just cut off there part way through a minute ago. So I think we got as far as the question. We said x follows a Poisson distribution. That value of lambda is its mean and its variance. Any sample mean, no matter what distribution it comes from, is normal mu sigma squared over n by the central limit theorem. So we can substitute those values in. That's our mu, that's a sigma squared over n, which we're going to find out. The sentence in the question gave us this probability statement here. It's less than, which is good. So we go for phi of our x value minus our mean over our standard deviation equals our probability. Anti-phi both sides there. This comes to negative because it's on the left 1.645. Haven't written down the phi there. Rearrange that, you get a value for n. It's got to be a whole number, so we just conclude finally for that one that n will be equal to 30.